The next thing we're going to talk about is bond dissociation energies, fuel efficiency, heats of combustion, and entropy. So this was where we started the thermodynamics, and here we were last time in the video. So starting with the standard heats of formation, there are so many chemical reactions in chemistry and thermodynamical processes where it's impossible to measure delta H. So a more efficient method is used to measure standard heats of formations, which is denoted by delta H, not F, for different substances, and these values are then used to calculate delta H for any reaction that involves those substances. So the standard heats of formation has the definition that the enthalpy change delta HF naught for the formation of 1 mole of substance in its standard state from its constituent elements, which are also in the standard states, is known as the standard heats of formation. As we discussed in the last video, standard conditions are the standard conditions set by the scientist. Usually the reactions to form a substance from the constituent elements can be referred as an hypothetical statement. The condition or the reaction statement or the chemical reaction equation is mostly hypothetical, and we can combine carbon and oxygen or carbon and hydrogen in a laboratory to make methane. For example, the heat of formation for methane is delta HF, which is equal to minus 74.8 kilojoule per mole, which corresponds to the standard enthalpy change for the hypothetical reaction, which is given. So secondly, each substance in the reaction must be in its most stable and standard condition, which is 1 atm pressure, and specified temperature, which is 25 degrees Celsius. So the next thing we're talking about is bond dissociation energies. So determining the heats of reaction from heats of formation is really very important and useful, and it gives a good answer to many of the problems. And to use that method, it's necessary to know delta F for each of the substance in a reaction. So this implies that vast number of measurements should be taken, and there are overly 40 million known chemical compounds. So it's in practice, though, only a few thousand HF values have been determined. So for these reactions where insufficient HF data, delta HF data is available, so it allows an exact calculation of delta H. It's often possible to estimate delta H by using average bond dissociation energies. So mostly the chemists use bond dissociation energies, which is denoted by D, and bond dissociation energy means that the amount of energy that is supplied to break a chemical bond, as it means dissociation in an isolated molecule in the gaseous state, and is thus the amount of energy released when the bond forms. So it equals the amount of energy released in the bond when the bond forms, and we don't look at it like if the bond dissociation energy and the standard formation energies are equivalent to each other. So although we didn't identify it as such at the time, a bond dissociation energy is really just the standard enthalpy change for the corresponding bond breaking reaction. And for the reaction between H and Y, for example, if you take it for instance H plus Y, then the delta H will be equal to D, bond dissociation energy. And when we say, for example, that the bond dissociation energy of chlorine or Cl2 is 243 kilojoule per mole, we mean that the standard enthalpy change for the reaction will be 243 kilojoule, because Cl2 is converted into 2Cl in the gaseous state, and the delta H will be 243. Bond dissociation energies are always positive because energy must always be put into bonds to break them. So that is a natural process, that is a natural instinct that tells us that the bonds, if they're about to break, the energy is required. And applying that Hess's law we've learned before, we can calculate an approximate enthalpy change for any of that reaction by subtracting the amount of some of the bond dissociation energies in the products from the sum of the bond dissociation energies in the reactants. So in the reaction of H2 with Cl2 to yield HCl, for example, the reactants have one CCl bond and one H to H bond, while the product has two H to Cl bonds. So H2 plus Cl2 in gaseous state is converted into 2HCl, and the bond dissociation energy of Cl2 is 243, and of the H2 is 436 kilojoule per mole, and that is that of HCl, which is equivalent to the product, or the sum. We can say the sum of the H2, individual H2 and Cl2 molecules. So we can calculate and approximate standard enthalpy change for the reaction by this formula. So the reaction is exothermic, as we know that the negative value of the delta H comes as an answer. So that is connected to the concept of fuel efficiency, and fuel efficiency and heat of combustion are closely related. Surely most of the forms of the fuels, we have learned those forms and we know those forms in our daily lives, but the most familiar of all exothermic reactions is the one that takes place every time we turn up the thermostat or drive a car, or we light up a match. So the burning of a carbon-based fuel by reacting with oxygen to yield H2O, CO2 and heat is the most common reaction we face in our daily lives. The amount of energy released on burning a substance is basically known as heat of combustion, and it's denoted by delta H C naught, or it's also known as the combustion enthalpy, delta Hc. C is indicated for combustion. Always remember that. And is simply the standard enthalpy change for the reaction of 1 mole of substance with oxygen. Combustion means the reaction with oxygen, which is the form of burning. So hydrogen, for instance, has delta Hc, which is equal to minus 285.8 kilojoule per mole, and methane has minus 890.3 kilojoule per mole. So to compare the efficiency of different fuels, it's so much useful to calculate combustion enthalpies, and we can know which fuel is better than the which fuel. So per gram or per milliliter of a substance rather than per mole is more useful combustion enthalpy calculated yet. So for applications where weight is important, as in rocket engines, the weight is much important because the rockets have to launch in the space. So hydrogen is ideal because its combustion enthalpy per gram is highest of any known fuel. So, and if you talk about for applications where volume is important, as in automobiles, a mixture of hydrocarbons is used. Compounds of carbon and hydrogen is known as hydrocarbons, and such as those which are present in gasoline are most efficient because hydrocarbon combustion enthalpies per milliliter are relatively high. So with the exception of hydrogen, all common fuels are organic compounds, whose energy is derived ultimately from the sun through the photosynthesis process of carbohydrates in green plants. So we know that the details are complex, but the total result of the photosynthesis reaction is basically the conversion of carbon dioxide and water into glucose plus oxygen, and glucose once formed is converted into cellulose and starch in plants, which in turn act as structural material, which we study in biology, for plants and as food sources for us, the animals. The conversion is basically high, and it's highly endothermic, and therefore requires large input of solar energy, and it has been estimated that annual amount of solar energy absorbed by the Earth's vegetation is approximately 10 raised to power 19 kilojoule, an amount sufficient to synthesize 5 into 10 raised to power 14 kilograms of glucose per year. So the fossil fuels we use, which is mostly coal, natural gas, petroleum, are derived from the decayed remains of organisms from previous geological eras. So both coal and petroleum are enormously complex mixtures of compounds. Coal is primarily of vegetable origin, and many of the compounds it contain structurally similarity to graphite, which is pure carbon. So we can say that all the hydrocarbons are related to the vegetation, and in the case of petroleum is a viscous liquid mixture of hydrocarbons that is primarily from marine origin, and natural gas is primarily known as methane, CH4, If you talk about coal is burned just as it comes from the mine. It's a rocky type structure, and from we can say that petroleum must be refined before use, but coal doesn't need any refining before using. So as the world's petroleum deposits have become more scarce, other sources of energy will be found to replace them soon. So hydrogen, although burns cleanly and is relatively non-polluting, has numerous drawbacks. Hydrogen can be used as a replacement, but it also has some drawbacks, which is low availability, difficulty in transport and storage, and low combustion enthalpy per milliliter, and etc. So let's talk about entropy. Sometimes in nature, some things happen naturally, and for example, water flows downhill naturally. We have to pump it uphill, and a spark is enough to initiate a forest fire. The ceaseless input of energy from the sun is required to rebuild the forest from carbon dioxide and water. Anyone who thinks about the world may wonder what determines the natural direction of the change. So entropy means randomness. Chemical reactions and physical processes in our daily lives occur when the final state is more stable than the initial state. So we can say that less stable substances generally have higher internal energy, which we've studied before, and are converted into more stable substances with lower internal energy, which means that energy is generally released in chemical reactions. At the same time, though, we have seen that some reactions and processes occur even though they have absorbed rather than released the energy. Here the example will be of the endothermic reaction of barium hydroxide octahydrate with ammonium chloride. So an example of the physical process that takes place spontaneously yet it absorbs energy is that the ice cube, how the ice cube melts at a temperature of 0 degrees Celsius. Ice spontaneously absorbs heat from the surroundings to turn from solid to liquid. So it's important to understand what the word spontaneous means in chemistry and thermodynamics. So in chemistry, a spontaneous process is one that starts without any help, or we can say that proceeds on its own without a continuous internal influence. So entropy means the molecular randomness, and the amount of molecular randomness in a system is known as system's entropy, which is denoted by S. We can see that the less randomness says that lower entropy, and more randomness means that higher entropy. So spontaneous process is favored by decrease in H, which is negative delta H, and favored by increase in S, which is positive delta H. And non-spontaneous process is favored by increase in delta H and favored by increase in delta H and favored by decrease in S. So we can say that the reactions have their own ways of proceeding, and there are different concepts which describe this thing. The next concept is the most authentic one. It's known as free energy, Gibbs free energy, and we must have been pondering about this, that how do we weigh the relative contributions of enthalpy changes delta H and entropy changes delta S to overall spontaneity of a process. Basic problem here is to understand what is a spontaneous process and what happens that a process occurs on its own. So to take both factors into account when deciding the spontaneity of a chemical reaction or other processes, we define a quantity known as Gibbs free energy change, which is denoted by delta G. It relates delta H and delta S by the equation delta G is equal to delta H minus D delta S. So we can say that the value of the free energy change determines whether a chemical reaction process or a physical process will occur spontaneously or not. If the G has negative value, free energy is released and the process is spontaneous. If delta G has no value or it's zero, the process is neither spontaneous nor non-spontaneous, but is instead at the equilibrium state. So if the delta G has a positive value, free energy is absorbed and the process is spontaneous. because the T delta S term in the free energy equation is temperature dependent, we can figure it out that some processes might be either spontaneous or non-spontaneous depending on the temperature. So at lower temperature, for instance, positive delta term might be larger than a favorable positive delta T delta S term, but at higher temperatures the T delta S term might be larger. That's an endothermic process that is non-spontaneous at lower temperatures can become spontaneous at some higher temperatures. So this factual data is actually what happens in the ice-water transition. Now you understand that what happens during this process. A temperature below 0 degrees Celsius is the melting of ice, and here the melting of ice is non-spontaneous because the unfavorable delta H term outweighs the favorable T delta S term, and at a temperature above the 0 degrees Celsius the melting of ice is spontaneous because favorable T delta S term outweighs the unfavorable delta H term, so that exactly at 0 degrees Celsius the two terms are balanced. So this is the entropy in chemistry. We can also solve the equation and to achieve T we can put delta H over delta S and we will get the value of T, and we can calculate those values with this formula, and